All right, so now I also need to give you a proof of A. And that has to do with this cosine function here. This is the property A. And so I'm going to do this by flipping it around, because it turns out that this numerator is a negative number. If I want to interpret it as a length, I'm going to want a positive quantity. So I'm going to write down 1 minus cosine theta here, and then I'm going to divide by theta there. All right? Again, I'm going to make some kind of interpretation. Now, this time, I'm going to draw the same sort of bow and arrow arrangement, but maybe I'll exaggerate it a little bit. So here's the vertex of the sector, but we'll maybe make it a little longer. All right. All right, so here it is. And here was that middle line, which was the unit. Whoops. OK, I think I'm going to have to tilt it up. OK, let's try from here. All right. Well, you know, on your pencil and paper, it'll look better than it does on my blackboard. OK, so here we are. Here's this shape. Now, this angle is supposed to be theta, and this angle is another theta. So here we have a length, which is, again, theta, and another length, which is theta over here. That's the same as in the other picture, except we've exaggerated it here. And now we have this vertical line, which, again, I'm going to draw in green, the bowstring. But notice that as the vertex gets farther and farther away, the curved line gets closer and closer to being a vertical line. That's sort of the flip side by expansion of the zoom-in principle, the principle that curves are nearly straight when you zoom in. If you zoom out, that would mean sending this vertex way, way out somewhere. The curved line, the piece of the circle, gets more and more straight. And now let me show you where this numerator, 1 minus cosine theta, is on this picture. So where is it? It's, well, this whole distance is 1, but the distance from the vertex to the green is cosine of theta, right? Because this is theta, so dropping down the perpendicular, this distance down back to the origin is cosine theta. So this little tiny bitty segment here, which is basically the gap between the curve and the vertical segment. So the gap is equal to 1 minus cosine theta. All right? And so now you can see that as this point gets farther away, if this got sent off to the status center, you would hardly be able to tell the difference. The bowstring would coincide with the bow, and this little gap between the bowstring and the bow would be tending to 0. And that's the statement that this tends to 0, as theta tends to 0. All right, the scaled version of that. Yeah, question down here.
The denominator also tends to 0, though?
The question is, doesn't the denominator also tend to 0? And the answer is yes. In my strange analogy here with zooming in, what I did was I zoomed out the picture. So in other words, if you imagine, you're taking this and you're putting it under a microscope over here, and you're looking at something where theta is getting smaller and smaller and smaller and smaller. All right? But now, because I want my picture, I expanded my picture. So the ratio is the thing that's preserved. So if I make it so that this gap is tiny, yeah, let me say this one more time. I'm afraid I've made life complicated for myself. If I simply let this theta tend into 0, that would be the same effect as making this closer and closer in, and then the vertical would approach. But I want to keep on blowing up the picture so that I can see the difference between the vertical and the curve. So that's very much like if you're on a video screen and you zoom in, zoom in, zoom in, zoom in. So the question is, what would that look like? That has the same effect as sending this point out farther and farther in that direction, to the left. And so I'm just trying to visualize it for you by leaving the theta at this scale, but actually the scale of the picture is then changing when I do that. So both theta is going to 0, but I'm rescaling it so that it's of a size that we can look at it. And then imagining what's happening to it. Okay, does that answer your question?
My question then is, that seems to prove that that limit is equal to 0 over 0.
It proves more than it's equal to 0 over 0. It's the ratio of this little short thing to this longer thing. And this is getting much, much shorter than this total length. You're absolutely right that we're comparing two quantities which are going to 0, but one of them is much smaller than the other. In the other case, we compared two quantities which were both going to 0, and they both end up being about equal in length. But here, the previous one was this green line. Here it's this little tiny bit here, and it's way shorter than the 2 theta distance. All right?